So, looking at this this problem here, they're asking, what is the electron configuration of hydrogen? What do we think? Sorry, go ahead. Yeah. 1s1, exactly. Now, you're like, goodness, how would I know? What does that mean? Well, the 1 is referring to the fact that we are in the first row, the first period of that periodic table. The S is referring to these first two groups of the periodic table. Let me jump to this slide here. So so we're doing hydrogen and neon. Let me just write them on the board here. Let me move the camera over so we can't see that. There we go, that works. Okay, so going from here, notice the structure of the periodic table. I won't give this to you on the test, but all you have to memorize is that if you're in the first two groups, that's the S block. Then when you get to the transition elements, this is the D block, so 3 through 12. Those are the D block. I'm going to explain to you what the D block is today. Basically, it's just some bigger orbitals. And then the P block is where you go from it's everything after the transition elements. So this would be the P's. So hydrogen is right here. It is in the first group, so 1. It is in the S block, so S, and it's the first position in the S block, so 1s1. There you go. Now if we do the orbital diagram, that's where you do the arrows. Each electron gets an arrow. So there's only one electron. Convention says you start with an up arrow. Remember the up or the down arrow? That just represents the spin these electrons have. Just convention says, hey, start with the up arrow. And there you go. That's simple. This is the orbital diagram when you're drawing out the actual arrows. So then looking at neon, neon is right here. So who thinks they know how to do electron configuration for neon? Carl, you want to go for it?
1s2, 2s2, 2p6.
2s2, 2p6, you got it. So all you're doing, just like when you're reading a book, you start in the top left-hand. Literally all we're doing is reading a book. That's basically all we're doing here. Like if you're lost, you're like, this seems impossible. I promise you, it's really as simple as just reading a book. You start in the top left corner, and you have to get to neon, you have to go from left to right, then go to the next line of the book, left to right, and then you stop once you get to neon. So to get to neon, we have to start at 1s. We then go all the way through the 1s, so that's why you say 1s2. There are 2 elements in the 1s. Then go to the next line of the book, 2s. There are always all the s orbitals, that's the spherical shaped orbital, they all hold 2 electrons. So 2s, 2. Then you keep going to the right. Now you're at 2p, and neon is in the 6th spot. It's at the very end of the 2p's. The p orbitals can always hold 6 electrons. That's why there's always 6 here. And that's it. Now, when you're doing the orbital diagram, all you're doing is, for the 1s, you just have one line or one box. And you always fill the off-bow principle. Say you fill the lowest ones first. So you fill the 1s first. Then we're going to place the electrons in that 2s orbital. That's what came next. And you go up, down. And then the p's, I said the p's can hold up to 6 electrons. That's why there are then 3 of these orbitals here. Each orbital can hold 2 electrons. So then you're at, and it was 2p. So what you're going to do, pay attention to how the order I put these arrows. The first electron goes here. The second electron doesn't go here. Hund's rule says you fill the empty orbitals first. So I said, imagine you're on the metro, and these are like empty seats in the metro. I said, somebody just took a seat next to you on the metro when there was empty ones. That would be weird, right? I don't care if she's a Hyundai, you have to take the empty seat. Or you could think of a hound. You don't put 2 hounds in the same cage. unless you have to. So now the fourth arrow, fourth electron, now we start pairing up. And that's it. Okay. That is reviewing the electron configuration. These are the two rules I went over, Aufbau, Hund's rule. So let's get into part two. So go and get your notes out. And basically, part two is just, all right, well, what do we do when we get to these bigger elements? And when you're doing the bigger elements, it really is, bless you, it's really like the same as when you're doing the smaller elements. It's just you have a longer path to get to the bigger elements. There's just more electrons that you have to place. Okay, so get yourself to the third row elements here. All right, so third row of the periodic table, period 3. These are the period 3 elements. So we start with sodium, that's all the way to the left, and then argon is all the way to the right. Now, if I were to actually write out the electron configuration of sodium, this would be the full electron configuration of sodium. I would go 1s2, 2s2, 2p6, 3s1. And you're like, that's a lot of writing. Like you're like, that actually takes a lot of time to write that. Is there a more efficient way to write that? And to make sure we're on the same page, you're like, how did you get that? Let me go back to this slide. Sodium is right here. So you start up here, 1s2, then go to the next line, 2s2, 2p, there's 6 of them, 6, and then 3s1. So the question is, can we speed up this process? Can we be more efficient? You can. There's something called the noble gas notation. So these are the noble gases right here, the very last column. So the shortcut is, if I put brackets, I can rewrite instead of having to write all of this, 1s2, 2s2, 2p6, that was the warm-up. That was neon here. Instead of having to write that out, I could just go brackets, neon, and that kind of like in algebra, you can say like x means this. That's sort of what you're doing. You're just saying, hey, that's neon. And then you write what is unique to sodium, 3s1. So that's what you're seeing here. So for the configuration for sodium, it's just brackets, neon, 3s1. And then for the orbital diagram, you're like, do I really have to draw out like a million arrows? It's like, no, same thing. You could just say brackets, neon, and then the orbital diagram, you put the electron arrow that's unique to sodium. So you just have that one arrow that goes with the 3s. How it would actually look, if I were to draw out the full orbital diagram, it would be like this. You'd have 1s, 2s, the 2p's, and then 3s. And you have to go like this, and you're like, goodness, I'm falling asleep right now. This takes forever, right? Oh my gosh, this takes so long. And I agree. So then, hey, let's just, instead of having to write all of that, you just say brackets neon. Because that whole thing is the orbital diagram for neon. You with me? Just a shortcut. All right. And then it's the same pattern here. So then magnesium is right next to sodium on the periodic table. So in the orbital diagram, you would just add another arrow for that electron. I would just add an arrow. Put an arrow there. And then you would say 3s2 now, because it's got another electron. Then you go to aluminum. Now aluminum, if I jump to this slide, aluminum is now over here. Now we're in the 3p's. So aluminum's right there. So now you have to add another set of 3p's. Notice how it's 3 different orbitals, because you can hold up to 6 electrons in the 3p's. Each orbital, represented by an underline, is an orbital. So now 3p1. Then silicone, add another one, 3p2. Phosphorus, add another arrow. Notice how Hund's rule says they take up separate orbitals first. So now 3p3, and then sulfur. Now we start pairing 3p4, all the way down to argon, where you're 3p6. Where argon is just like neon, but it has the additional 3s2 and 3p6. Okay. So in other words, the bigger elements really are just longer than the smaller ones, but not really, because you can do the noble gas notation. You can just say the nearest noble gas. All right, let's move on to some of the bigger ones. So when you get to the fourth row of the periodic table, so when n equals 4, that means we're in the fourth row, the fourth period, otherwise known as the fourth shell, that fourth energy level. What you'll notice if you look at your periodic table is in that fourth row, we now have you now have those transition metals. And so the question is, well, how do I accommodate the electrons of all of those transition metals? Where do you place them? How do we adjust our electron configuration? Well, this is where we had the introduction of a new orbital. So we talked about the s orbitals that are spherical. The p orbitals, they were a dumbbell shape. I told you, like p, and a d, they're like upside down and flipped. That's how you can remember the shape of the p orbital. Well, the d orbital is a cloverleaf shape. Cloverleaf. I don't really know how you remember that, but I don't know. It just is kind of there. I guess these kind of all look like, maybe you can do like, oh, that kind of looks like a D, and that looks like a B, which is just a D flipped around, and I don't know. Yeah. You got something?
I was gonna say it's like 4-leaf clover and use the fourth letter of the alphabet.
Oh, wow, that's deep. It's a 4-leaf clover. This is 1, 2, 3, 4, and D is the fourth letter of the alphabet. Wow. It's life-changing. Carl, you got something else?
You can also think about how like the 4-leaf clover is representing like the Ireland.
Okay.
Since Ireland's capital is Dublin.
Okay. 4-leaf clover identified with Ireland. Ireland's capital is Dublin.
Like the last letter of Ireland.
Last letter of Ireland's D. You got plenty of things to help you remember it. So, anyways, notice how you see 5 different shapes of clover leaves. This is because this is where it becomes very difficult to imagine in 3D space how to like picture all of this. Basically, what I want you to understand is you can fit up to 10 electrons in the d orbital. Up to 10 electrons. Now, looking at the transition elements on the periodic table, why would that make sense that you can hold up to 10 electrons in the d orbital? What do you notice about the transition elements? Look at your periodic table. Start counting from 3. Emery, yeah? There's 10 of them. Every time you go across a period on the periodic table, you count 10 transition elements. That is why you can hold up to 10 electrons. 2 electrons can go in each of these 5 orbitals, adding up to 10. So that's why there's 5 of them. Bless you. All right. So you're like, okay, what does that mean exactly? Well, all right. Coming back to the ARF-bow, the off-bow principle, we always go from low to high. So this is what your orbital diagram would look like now. You go 1s, 2s, 2p, 3s, 3p. We've seen these before. Now we include, now you're in the 4th row of the periodic table. So now you go 4s, 4th row. But this is the weird thing with when you get to the transition elements. Notice how this has a 3. The d orbitals are always 1 number behind. Basically, the reason why is sometimes, like the shape of the d orbital, sometimes the electrons in the d orbital can actually be located in the 3rd energy level. It's kind of weird. Other times they can migrate upwards. They're still higher energy. The 3D are still the higher energy electrons, but they are technically in the third energy level. So when you're writing out the orbital diagram, you go 1s, 2s, 2p, 3s, 3d, 4s, and just remember it's always one behind. So you go 3d. This is trying to show you like the order you go. So you go 1s. If you write, so basically how you do this is if you go 1s, 2s, 3s, 4s, 5s. And then the p's, you go one down and over, 2p, 3p, 4p, 5p. And then the 3d, you just go, like, notice the pattern here. Now we go 3, like you're in a ladder, and you go 3d, 4d, 5d. The order that you fill, you then go 1s, 2s, that's the order. Then you would go 2p, 3s. Then the next one, you go 3p, 4s. Now you go to 3d. And it feels like that. That's the pattern with it. Okay? Don't worry about the F's. For our class, you don't have to do the F ones. The F ones are when you get into the lanthanides and the actinoids. Okay? All right. So what does this look like, practically speaking, for the actual electron configurations? Well, this is the electron configuration of the fourth period elements. So if we start from the very left, potassium is the very first element in the fourth row. Here's potassium. Its electron configuration. So if you wrote out the whole thing, this is the whole thing, right? And you're like, that takes a long time. This would be like if you start with hydrogen and you trace out the whole path, that's what it would be. Or if I just say this part, that is the electron configuration of the nearest noble gas, which is argon. 1s2, 2s2, 2p6, 3s2, 3p6. That's the electron configuration of argon. So you go brackets argon, and then 4s1. That's the unique thing for potassium. So nearest noble gas of potassium is argon. Okay? And a similar thing with the orbital diagram. If you're going to do the orbital diagram, you can just go argon, and then you can go 4s, and just put one arrow. Rather than having to draw out the arrow for every single one. Okay? So then if we do the other elements here. Calcium is right next to potassium. So now we go 4s2. Now this is where it gets a little weird, just a little bit. Now we encounter our first transition metal, Sc. Sc is right there. 4s2, now it is 3d1. So you're still going in order, right? You're still going and you hit the transition elements, but instead of saying 4d, you just go one behind. You say 3d. Okay? And then everything, all the rest of these elements, these are all transition elements. So we end here at 3d9. Okay? The very last transition element would be like zinc for that period. Zinc would then end at 3d10. Okay? Are we good on this slide? Hopefully you're seeing the pattern here. All right, let me show you the orbital diagram. We're looking at gallium. So gallium is where you then get into, now we're still in the fourth row, fourth period, but now we've gotten out of the transition elements and we're right here. So this is where we're looking right here. There's gallium. This is the electron configuration. If I start from here to get to gallium, you have to do that whole pathway to get there. And notice how long it took me to trace that whole pathway. If you wrote out that whole pathway I traced out, it would be this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then now 4p1. We end at 4p1. The shortcut would be, hey, this right here That is the electron configuration of our closest noble gas, which is argon. Then you add what is unique to gallium. Well, that's this stuff right here: 4s2, 3d10, 4p1. 4s2. Remember, you're always one behind, and you can see that this is labeled pretty nice. So you can see that you're always one behind on the D's. 3d10 and then 4p1. Okay. Notice how this would be the full electron configuration for it, or orbital diagram for it. Again, the shortcut, the quicker way you could do it is this whole thing right here. That's the orbital diagram for argon. So you could just put brackets argon, and then you only have to do 4s, 3d, and 4p. Yeah.
Why do we use the argon instead of like
Oh, are you saying like this one? Like krypton? Or
maybe like next to it?
this one right here? Yeah, the question, okay, like why can't you just do like zincs, bracket zinc? I don't have a good answer for that. That's just not how the powers that be decided to do it.
But do you always use?
The convention is you always do the nearest noble gas. Yeah. I agree it would be a lot easier if you could just do like the element directly next to it. I just wasn't in that meeting. I didn't get invited. Yeah, Victor.
But for the smaller ones, like let's say, like on the periodic table, like lithium.
Yeah,
Would it be
like
useful
lithium.
to use helium as an example for that?
All right, yeah, so if you're going to do lithium, could you do the noble gas notation? And you could, but like, all right, so lithium, if you did the longhand way for lithium, you would do 1s2 and then 2s1. This is the shorthand for lithium. This right here, that is noble gas notation for helium. So you go helium, 2s1.
So you could, right?
You could, but like that really isn't any less writing. So that's why I didn't teach you the shorthand last time, because we were only last time doing up through the 2p's. It just wasn't really as relevant. But once you start getting these bigger elements, you want a quicker way to do this. Okay. All right, we good here? So then let me show you an even bigger element. So this is where I'm showing you krypton now. So krypton, this is us finishing the fourth row, the fourth period of the periodic table. Bless you. So looking at krypton, krypton is where you go all the way to the end of the 4p's, 4p6. Okay? So this should be the super long, like the full configuration. The shorthand would just be, hey, that's the very nearest noble gas. That would be argon. You could go brackets argon, 4s2, 3d10, 4p6. Not as much of a shorthand because you're kind of at the very end of it, but it still is shorter than writing that whole thing out. Yeah.
I still don't understand why you
It's just it's a quirk of like how the electrons and the transition elements behave. Basically, that cloverleaf shape, the electrons in that cloverleaf shape, they technically reside in the third energy level, in that like how far they are from the nucleus. They're technically in the third energy level, but like they're technically, like, these electrons have higher energy than in the 4s. So it's just kind of a quirky thing that happens with the transition elements. There isn't, I can't really think of a better way to describe it, or I don't even fully understand beyond just that it's just always one behind.
That's for every one of them.
For all the 3D. So if I go back to this slide, see how we're in the fourth row, it's 3D. Here's the fifth row, it's 4D. 6. So it's just remember it's one behind. Okay. Yeah, Johar?
How do I know which one's after before S2?
How did you know 4s2 came after argon? Yeah.
Why didn't I put like 3s2 or something?
Okay, so yeah, here was argon. So then we were doing, on that last slide, we're doing krypton. So follow the path. After argon, you go to the next line of the book, which is 4s2. So that's why then you went 4s2. Then you just go in order. Then 3d10, and then 4p. Okay. So what you have to memorize is the first two columns are the S's, transitions are the D's, and then everything after the transition elements are the P's. That's what you have to memorize. Everything else just goes in order. Okay. All right, something new here is the number of valence electrons. So I could ask you, hey, how many valence electrons do we have here? And you would focus on the highest energy level. This is where, like, getting into, like, okay, well, what is, like, the 3? Like, how does that factor into, like, maybe how we would interpret this stuff? The outermost electrons would still be, like, the high, like, when we say valence electrons, we're talking about the electrons in the outermost energy level. That's where you focus on the 4. So 4 and 4. So you still have 2 plus 6 is 8. You still have 8 electrons that are in that outermost valence shell for something like krypton. Or if I were to go back to argon, the number of valence electrons for argon would be 2 plus 1 would be 3. Wait. Or this wasn't argon, so this is gallium. I was like, that's not right. Gallium. Okay, it would be 3. Because because the highest energy level are these 4s. The 3d10, these wouldn't be considered valence electrons because they're still technically part of that 3rd energy level. Okay? It's a little weird. It's just a quirk of how the electrons and the transition elements behave. Choose, yeah, you count the exponents of the highest energy level. Okay. And then the orbital diagram. So this is the full orbital diagram, but we just keep going in order. So 4s, 3d, 4p. You just keep going up in order. Okay. All right. So going to your worksheet, I messed some stuff up, so we're gonna have to do some adjustments here. So if you look at, let me zoom in a little bit. Germanium here, you'll notice how it stops at 3D, but germanium is all the way here in the 4th row. And so you're like, what? I think I could have you try to squeeze in a 4p there, but let's just have you change GE to, let's do copper. So just make this copper, Cu. Okay, so for number 4, make that copper. Let's make number 5, make that titanium, Ti. And then let's make this one, let's make number 6, make that chlorine. So CuTiCl. I'll write that down. And I think that would fix any issue here. Yeah. Everything else should be okay. So yeah, go ahead and finish up the rest of this worksheet. And let me know if you got questions.